Hello students, welcome again in lecture series of robotics and automation. This is the fourth lecture and it is on degrees of freedom and workspaces. Learning objectives are: by the end of this lecture, students will understand degrees of freedom in robotics, learn how degree of freedom affects robot movement and flexibility, understand robot workspaces and their types, and explore the relationship between degrees of freedom and workspaces. Introduction: why is degree of freedom important? To understand degrees of freedom, let's take simple example. So think about your arm. You can move it up and down, you can move it left and right, and you can bend your elbow and rotate your wrist. So each of these movements adds flexibility to your arm. Now imagine if your arm was fixed in place and could only move in one direction, it would be much less useful, right? Similarly, in robotics, degrees of freedom defines how freely a robot can move. The more degrees of freedom a robot has, the more complex tasks it can perform. But movement alone is not enough. A robot also has a workspace which tells us how much area it can reach and operate within. Some robots have a large workspace while others are designed for smaller areas. Now, what is degrees of freedom? Definition: degrees of freedom refers to the number of independent movements a robot can perform. A human arm has 7 degrees of freedom. The shoulder, this is a shoulder, it has 3 degrees of freedom. It moves forward, backward, up and down, and it can rotate. Also, elbow has 1 degree of freedom. This is elbow, it has 1 degree of freedom. It bends and strengthens. Then this is the wrist. Wrist has again 3 degree of freedom. It can rotate, it can bend, and it can move sideways. The robotic arm may have 3, 4, 5, or even 6 degree of freedom depending on its design. Now, how degree of freedom is measured in robots? In a three-dimensional, that is 3D space, a robot can move in 6 different ways. Translational or linear motion, that is moving from one place to another place. There are 3 translational motions. First is a moving forward and backward, that is movement along x-axis. Second is a moving left and right, that is movement along y-axis. And third is a moving up and down, that is movement along z-axis. And 3 rotational motions are there, that is rotating around an axis. First is a rotating left and right, that is yaw motion, like turning your head left and right. Second is a rotating up and down, that is pitch, like nodding your head up and down. And third is a rotating sideways, that is rolling motion, like tilting your head to touch your shoulder. Now, degrees of freedom in different types of robots. So this is a fixed base robot, that is a stationary robot, and these robots are attached to a base and do not move from their position. Their movement is limited to their arms or end effectors. So common degrees of freedom values are 3 degrees of freedom. Simple pick and place robots has 3 degrees of freedom, and advanced industrial robotic arms for flexible movement has 4 to 6 degree of freedom. For example, SCARA robot has 4 degree of freedom, which is used in assembly lines for electronics. Then 6 degrees of freedom industrial robots are used in welding, painting, and packaging purpose. One equation is there: more degrees of freedom means more flexibility to perform tasks. Then second is mobile robots, robots that can move. So these robots are not fixed to one position. They can move in the environment using wheels, legs, or flying mechanisms. Common degrees of freedom values are 2 degree of freedom. Simple wheeled robots has 2 degree of freedom. 3 to 4 degrees of freedom. Humanoid robots, that is legs and wheels, robots has a 3 to 4 degree of freedom, and drones and autonomous robots has 6 degrees of freedom. Examples are autonomous cars having 3 degree of freedom, move forward, backward, turns left, right, but no up down motion is possible in autonomous cars. Drones have 6 degrees of freedom because it moves in all directions and rotates freely. So more degrees of freedom is equal to more movement possibilities. This is another equation for degrees of freedom. Now, what is a robot's workspace? Definition: a robot's workspace is the total area it can reach and operate in. There are two types of workspaces. First is a reachable workspace. The maximum area a robot can reach with its arm or body is called as reachable workspace. For example, a robotic arm in a factory has a limited reach based on its size. Second is a dexterous workspace. That is the area where the robot can work with full control in any direction. It's called as dexterous workspace. And for example, the robotic arm can move freely in front of it but may have limited movement behind its back. Types of robot workspaces. This is the first type, Cartesian workspace, that is a rectangular shape. Shape is a rectangular or a cubic workspace due to linear motion along x, y, and z axis. Reach: the robot can move precisely in straight lines along its three perpendicular axes. Motion limits: movement is restricted to three linear axes, limiting rotation and flexibility. Requires more space due to its rigid structure. Example is used in CNC machines and 3D printers for precise material deposition and cutting. Advantage is a high precision and stability for manufacturing and material handling. And limitation is slow movement compared to rotary based robots and takes up more space. Second type is a cylindrical workspace. Shape is a cylindrical workspace due to one rotary motion, base rotation, and two linear movements, that is vertical and radial linear movements. Reach can extend and react. Reach can extend and retract radially while also moving up and down. Motion limits: can rotate horizontally but not as flexible as articulated robots. Limited reach compared to Cartesian robots. Example used in automated material handling and machine loading and unloading purpose. Advantage is a compact design with a good vertical reach, and limitation is limited flexibility in lateral movements. The third type of workspace is spherical workspace. Shape is a spherical workspace due to combination of rotary and linear movements. Reach can rotate horizontally and vertically, allowing movement within a spherical range. Motion limits: can cover a large area with fewer joints but has less precision than Cartesian robots. Limited flexibility in linear motions. Example is used in welding robots and paint spraying applications. Advantage is a wide range of motion with fewer mechanical parts, and limitation is not suitable for tasks requiring high precision. And fourth type is articulated workspace, that is multi-joint robots. Shape spherical or complex workspace due to multiple rotary joints. Reach can move freely in multiple directions, mimicking a human arm. You can see in a diagram. Motion limits: offers high flexibility but programming is complex. Requires more space for operation compared to SCARA or Cartesian robots. Example used in automated assembly lines and robotic surgery. Advantage is highly flexible and versatile for complex tasks. Limitation is expensive and requires maintenance due to multiple moving parts. Then the fifth type is SCARA workspace. Shape: SCARA robots have a cylindrical workspace, meaning they can efficiently operate in a flat horizontal plane with some vertical movement. Reach: the robot can extend and retract its arm within a circular range, allowing it to perform precise pick and place tasks. Motion limits: SCARA robots have limited vertical movement but excellent horizontal flexibility. The rotation of the arm defines the range of motion, making it suitable for small and compact workspaces. Example used in electronics manufacturing, where it assembles circuit boards with precision. Advantage is the design allows fast and repeatable operations in confined spaces, and limitation is not suitable for tasks requiring high vertical reach or extreme flexibility. Thank you very much.